Okay, so welcome to first day of class. So I was. Let me see if I can. Unlike my other classes, I'll probably use two webcams for this course because I'm going to be talking a lot, not always writing a ton on the paper. So I think it's better. In most classes, I'm just constantly writing, so them students just seeing the top of my head is probably doesn't matter that much, but let's see here. I believe I can add. Let me see here. I believe that's. I will resize it. There. That's good. Okay. Let's see. Where do I want to put this? Yeah. Okay. Somewhere out of the way. Let's see. I don't tend to write up in this corner. There we go. This is better. Okay. So anyway, so welcome. I already have it on camera. Here's textbook. I'll talk more about the textbook here in a second and how much, how strictly required that is, which the quick answer is not that much. So anyway, welcome to the course. The first thing I'll say before saying anything else is like this is going to be a fun course. So there should be no panicked emotions about it. This should be fun for both of us. It'll be fun for me to teach it, and hopefully it will be fun for you too. The structure is going to be a lot different from typical math course, obviously. So, I am not totally dead set on exactly, I don't have the exact number of assignments that you're going to have through the semester or whatever. I think what I will do is there will be a midterm and a final, and there may be two midterms and a final, but the midterms are less like a math midterm and more like a writing assignment. So there will be a component to the midterms that do ask math questions, although I might ask you to say, for instance, show some technique that was learned from the discussion. So how, like for instance, how might an Egyptian do this multiplication problem? Those sorts of questions will be asked like on an exam, but also the exam will include some kind of writing component where maybe you're asked to write a quick 1 or 2 page essay on some particular topic that we've gone over. So the structure is definitely a lot different from most math courses. I was bad. I didn't finish putting the syllabus up on the page today, so I'll do that later tonight. So that when you go to the Elms page for the course, the default page listed should be the syllabus page. So that is going to be like kind of a central repository for all of the info for the course. So anyway, that's the quick version of what sorts of assignments you can expect. That is, it's not going to be typical. There's not going to be any quizzes. There's not going to be any strictly synchronous assignments, period. Meaning, when I say strictly synchronous, I mean you're not going to be asked to show up at some particular time and have a limited amount of time to do some assignment. So every assignment you will have days to complete. At least in this course, probably at least 48 hours to complete any given assignment. So both, since the midterms are going to have a written component, you're obviously going to have plenty of time to do that. And the other part of the midterms themselves, like the more, the questions where you're actually doing some kind of computations, you'll still have, a couple days to do those as well. So everything will be take home in the sense that you're going to, do work, either writing or math work on your own paper and scan it using your phone and upload it to Elms as a PDF. So, and you're going to have plenty of time to do that. Like I said, no strictly synchronous anything. Which also means there's no assignments due like during these lectures. So And since these lectures are YouTube live streams, they're automatically uploaded and will be, on the YouTube channel immediately following the lecture, so you can watch them whenever you want to. Let's see. So off the top of my head, like I said, I don't have the exact grading breakdown of how it's going to work between the assignment groups, but basically there will be small homeworks, which could be, short, couple paragraph writing assignments, and could also include some calculational problems. Some of those problems will come from this textbook, but I'll say that the textbook itself, like any problem I assign, I will tell you. I will either show it on camera during lecture, or I will post pictures of it to Elm. So if your plan was that if you felt like you needed the textbook strictly to see assigned problems, don't worry about that. I will take pictures if I need to. I chose this textbook. There was a list of recent textbooks that had been used by other instructors for this course. The problem was that the more popular choice was this massive tome. It's like 3,000 pages or something ridiculous it seemed like a great book, but it was literally just kind of just like a giant like math encyclopedia / dictionary of math history stuff, which is fine, but as far as using it as a reference goes, you can always look things up, either on Wikipedia or elsewhere on the internet. So it wasn't, I don't know, I don't think it didn't seem that useful for me as far as structuring a course around it, but this was kind of an interesting choice, and so I went with this because this kind of does a good job of jumping all over the place, starting at like 1800 or 2200 BC and going all the way to. So that's another thing that I'll get into here in a second is the challenge in doing math history versus other types of history. But the main chunk of like the meat of this course will take us all the way up to about 1800. So starting at about, 2300 BC and going all the way to 1800 is the main chunk of the course. After that, it's a little rough, and I'll mention that in a second. So if you have any like structural questions about the exam, or not the exam, the course in general, just let me know. You can ask those questions whenever, and I'll answer them as they show up. Using text fine for homework. Again, so like a lot of the homeworks are going to be a ton of writing, so you can use tech for that just as well. Obviously tech is perfectly fine for the math portions as well, but yeah, so that's perfectly fine. So if you have any general course questions that maybe I am missing or neglecting, or you just have questions about, you can let me know. But the main thing I wanted to say is the goal is basically to get us from the dawn of mathematics all the way to about 1800, and then what we do after that is there's some choices to be made. I probably won't follow the textbook past that point because they have some specific applications they want to go into that I'm not going to go into. I actually probably, because I'm a geometer, I'll probably go in the direction of geometry post like 1850 or 1830. So that might be what I do near the end, depending on where we get to and what's going on. I also might have a little survey or something, and just poll you all on what you would want to see from that. So there's a lot of questions you might have about like how involved the math is. So I'm going to, at various times when we're going over this stuff, I will go over proofs of various things, and some of the proofs will be stuff you've not seen, and some of the proofs could be pretty complicated, but I'm going to be showing you the proofs, right, for the mostly for the historical value and not necessarily going to be asking you to reproduce those kinds of things. So if you don't fully understand some of these things that are discussed, as far as like exactly the math that's going on, as I'm writing it down, it's not the biggest deal. Of course, you ask any questions you want over, to clear up any confusion, but you don't have to panic or anything if we're going over some topic and a proof gets a little involved and you're wondering like, oh, like do I need to know, like do I need to be able to reproduce this from memory with no help? And the answer is no, to that. So anyway, like I said, today is just kind of the general intro. So if you have any questions I haven't addressed about kind of the flow of the course. Format is obvious now. It's going to be these YouTube live stream lectures. So Monday, Wednesday, Friday, 3 to 3:50, we'll be doing this. And like I said, it should be, because it's about a 50-minute video. YouTube's been pretty good about automatically uploading those within. They'll show up on my channel within probably an hour or so. But even if they don't show up on the channel, they should be accessible through the link that I give out in Elm's announcements, like immediately, pretty much. So, so you should basically, the second that lecture is over, you could rewatch it or watch it for the first time, from then on, and that will show up on the course YouTube channel, which is this channel. I will later on, maybe once every 2 weeks or something, I'll fold all the lecture videos up to that point into a playlist, just so that when you're navigating the channel, you can, if you want, you can just click on the playlist and watch everything. So yeah, every couple weeks I'll just try to fold the last 6 lectures into an ever-growing playlist of videos that contains all the lectures for this course. And so that's the plan. So that's the format. But as I said, this is a fun course, so it's not, the workload will be lighter than a typical course. I probably won't assign your first homework for like a couple weeks. I don't know, maybe in like a week and a half I'll have some small assignment or something. But anyway, so as I mentioned, here's the textbook. Like I said, it's actually a pretty interesting book. I liked this approach better than the massive tome of let's just list every single like mathematical thing in chronological order. So anyway, but how closely am I going to follow it? I'm going to follow the overall outline for the most part, but I'm going to show you plenty of the relevant parts of this, like on camera or written out. And so it's not absolutely. I know it says for the course website that it's required, but it's not 100% required in the sense that yes, I'm gonna follow it. So it's nice of you to if you have it, you'll see exactly what I'm going to talk about, basically, because I'm going to follow it more or less in chronological order. But anything's posted from it, like in the form of graded assignments, I will post. Syllabus is not on Elms yet. It'll be on Elms later tonight. And if you've sent me an email in the past day or two and I haven't responded, I'll respond. I'll go through later. I have a huge backlog of emails because for whatever reason, a ton of people this semester don't have Elms access or getting it late or whatever's going on. The point is that like I had a flood of emails in the last couple of days from students that were needing Elms access or didn't have Elms access, and so they had no way of getting the links to stuff. So it was so I've been slowly going through all my emails. So if I haven't gotten to yours yet, then I will get to it soon. But yeah, I'll post the syllabus on Elms later today, which will include the full breakdown of how the grade's gonna go, and what, like the list of the assignment groups. Basically, there's no quizzes, so there's just homeworks, 2 midterms, and a final exam, which is going to be the same flavor as the midterms. There will be some computation aspects or some math, conceptual questions. So there will be math component, and then there will be written component. Okay. All right. So, I think that's all I wanted to say about the syllabus. Like I said, that it'll be substantially less confusing when I post syllabus later today. Um, in the meantime, I was going to go ahead and basically go over, what are some of the big challenges for talking about math history, because it's um, it's more complicated to deal with than maybe other sorts of. So just thinking about the history of subjects in general, or what should I say? Um, if you compare the progression of math to some other fields, the only field that is kind of sort of similar in progression, and you'll see what I mean later, is physics. So these facts that I'm about to say about math are true, like 70 to 80% for physics, but they're not really true for most other subjects. So here's an example. All right. So as I mentioned, we are going to start with the dawn of mathematics, for like 4,000 years ago, so 2200, 2300 BC. We're going to go all the way to 1800, and then it gets really hard to continue, and we're going to have to specialize and basically pick a path. And even when we do, it's going to be hard to delve into it really, and there's a reason for that. So here's the thing that separates math, and to a lesser extent separates physics from other sciences, other disciplines. So if you're in elementary school, right, and you are being taught out of an elementary school science book, um, if you open up, say, a section on biology, or you look at an elementary school biology textbook, the information that's being presented to students, and this is not just true of elementary school, this is true of grade school in general. So elementary school, middle school, high school, whatever. If you pick, say, biology textbook, then you're going to be seeing brand new, like cutting edge information presented to students. Now, of course, it's not going to be written in technical language, but cutting edge in the sense of, right, like imagine, for instance, right, so DNA was co-discovered in like the 50s, I think. So, so for instance, any biology textbook, post then is going to mention DNA, for instance, right? And so, that was cutting edge like 70 years ago. You'll see why I'm mentioning this specifically for math, because if you go back to math that was being done in the 1950s, it's far, far beyond, anything that is taught to, say, undergraduate math majors. For the most part, right? Maybe if you're a super duper duper motivated math major, if you're into applied math because of the tie-in of applied math with computational stuff, and computers not being a thing until much more recent, then this is less true. So this is less true for applied math that is really really focused on computational things. So applied math, scientific computing, what I'm saying is a little less true. But for pure math specifically, this is very true. That the pure math being done in the 1950s is something that as an undergraduate you do not, as an undergraduate math student, right? I'm not talking about just an undergraduate in general. An undergraduate math student you just don't touch. So another way of looking at it, right? As I said, if you're a grade schooler and you open up pretty much any other discipline's textbook, the information you're reading is brand new. In fact, it's brand new enough, and this is obvious. This is sometimes seen as a complaint about a certain discipline, that if you open up old textbooks, right? If you open up an old bio textbook from the 70s or 60s or something, then a lot of the information in those books is probably going to be wrong, right? Not just like slightly inaccurate or maybe not totally right, but like some of it will just be flat out wrong. That's not really what occurs with, say, math textbooks, right? It doesn't work like that. And the problem is that math is basically one of the oldest disciplines. I mean, it's basically the oldest, like, continuous discipline that's been practiced by humans, because math didn't require a whole lot of technology. It wasn't something that required some like technological advancement to be able to get to the next step. Really, that's just not how it worked. You know, if the ancients had figured it out, the ancients could have been doing, you know, differential equations, right? Like there's nothing stopping someone 3,000 years ago from working on differential equations. Right? There was no technological limitation there, really. So anyway, so the problem here is the following, right? If we just follow the progression of, say, high school mathematics, or you know, even middle school mathematics. So when students are first taught algebra, right? And we'll say that, okay, they've learned basic algebra and they've gotten to, you know, the quadratic formula, right? So this is high school math. Quadratic formula, though, is thousands of years old, as we'll see. It has been known for a really long time, you know, possibly as many as like, you know, 4,000 years ago, the quadratic formula was known. So, you know, that's 4,000-year-old math that you're learning in high school. If you're a motivated student, by the end of high school, you've gotten through, you know, Calc 1, Calc 2, you know, or Calc A, B, and BC. You know, calculus was co-discovered by Newton and Leibniz, right? And there's a lot of other contributors there, Bernoulli and some later contributors in the 1700s. But the point is, like, when you're doing calculus, right, which is like the pinnacle of high school math, you're doing math that's over 300 years old, for the most part. Now, there's some aspects, there's stuff that's been brought in to make certain, like, the development a little smoother or seem a little bit nicer that came a little bit later. But for the most part, you know, calculus as a subject is, you know, over 300 years old. So if you're if you're a motivated high school student, the absolute pinnacle of math that you learn in high school is still 300 years old. Compare that with any other subject, right? If you're learning 300-year-old biology, well, you know, you're essentially learning alchemy or, you know, like shamanism or something. 300-year-old biology basically is not even a science, right? So that's a huge difference right there. Of course, say you decide to go into math, right? At university, you're a math major at university. So first couple of years you take, you know, any remaining calculus courses you need, differential equations, linear algebra, things like that. All that math, right, is old, hundreds of years old. And so you might not get to it. I mean, you know, if you know much about abstract algebra and the development of abstract algebra and how, you know, Galois was, you know, kind of along with some other mathematicians, kind of the developer of, you know, modern abstract algebra. All this stuff happened in the early 1800s. And so, you know, you're not going to get to a description of Galois theory and stuff. This is like the end of a program, and you know, this is a 400 level algebra course as an undergrad. In fact, if you forget about undergrad for a second, let's, you know, continue on to graduate school. If you go to graduate school to get a PhD in math, when you are taking your first year qualifying courses as a PhD student in math, you're still studying math that is hundreds of years old. You don't get to math that was done in the last 120 years until you're basically ready to start reading for your like your preliminary oral exam. Like that's when you're getting to within. I mean, so depending on the field, I was going to say, so there's I guess by the time you finish your qualifying courses, you're doing math essentially that was done the last 100 years, like turn of the century, like 1900s. So, you know, the second that like if you take your first like real analysis course, graduate real analysis, that stuff is essentially about 120 years old. Roughly. Now, again, there's parts of it that are newer. There's parts of it that were done in like the 30s and 40s. But for the most part, yeah, you're studying math still that's roughly 100 years old, maybe a little bit less. Some fields you get a little bit newer than that, but it's not, you know, you're not technically doing, you know, ready to read cutting edge math until you are right about to start your, you know, reading for your dissertation, to figure out what's going on in whatever topic you've decided. And so my long-winded explanation there is to show that it's really, really different from other fields because of just how dense it is as a field, because it has existed for so long, because it didn't rely on technology. You know, most other disciplines are extremely new in comparison to math. And this is the reason why our main discussion of the history of math has to stop around 1800, and then we have to get more specialized, and what I include I have to cherry pick and go here and there, because there's no possible way in a one semester course to going from 1800 to modern math would take far longer than a single semester. Just that, you know, just going from 1800s, you know, like 1800 to now, take a lot longer than the entire rest of the history of math, because it's so dense and things became so specialized. Where, you know, previously in generations, like people like Newton and Bernoulli and Euler and Gauss, and these people were able to be masters of several fields of math at the same time. But that sort of thing became completely impossible. You know, and essentially, you know, you'll hear Henri Poincaré is, you know, he's called sometimes like the Last Universalist, and he died in 1912, I think, because he basically excelled in every single field of math as it existed during his lifetime, and he was kind of the last person that was true for. And you know, there are still mathematicians that are good at several disciplines, but not like in the 1600s and the 1700s. It was possible to literally be a master in every single discipline of math, but it's just not possible anymore, because things are so specialized. It would take so long just to read, you know, the required, like, just to get caught up in a single tiny subfield of a field in math, that it's just not really that possible to do anymore. And so things specialized so much after 1800 that a treatment, like from up to 1800, from like 2200 BC to 1800, we're basically going to go essentially in chronological order, and we're going to be meticulous and cover basically every mathematical development, like in order. That is pretty much impossible after 1800, because, like I said, things get so dense and so specialized that it would just be impossible. It would also it's a challenge already to try to relate some of this stuff, because, as I said, once you get to the 1800s, the math that you're talking about is stuff that is advanced material reserved for, you know, some of the last undergraduate courses that a math major takes. So this is, you know, this is one of the main challenges in covering history of math. But we won't get to that issue until later, till near the end of the semester. The question then is, what is good starting point? So there's really nice, let me actually find a really nice kind of, yeah, here's a nice description. And here, I'll put it here on my dock camera. So for instance, this is an example of Egyptian math. Okay. So here's what the actual papyrus looks like. So there's two main sources that we know of for Egyptian math. There's the Moscow Papyrus and there's the Rhind Papyrus. The Rhind Papyrus is the most famous and has probably the largest amount of info on it. The other one has like kind of one interesting problem, but everything else is fairly uninteresting. But the Rhind Papyrus is noted for this, what's going on here. Now, so what is it that's going on? I'll write this out in a second, but you might notice that, okay, like There's some recurring symbols here. But what is being done? So what's being done is a multiplication. All right, and so it's funny that I'll just quote what is said here about the Rhind Papyrus. So in the intro to the Rhind Papyrus, the author says the following. So the reader of the Rhind Papyrus is promised a thorough study of all things, insight into all that exists, knowledge of all obscure secrets, which sounds like a pretty awesome way of selling your papyrus as like the greatest textbook ever. But it turns out it's actually just a sequence. It's like a solution manual to some problems that were intended for scribes to be able to solve. And so these scribes were entrusted with things like needing to compute like how many bricks needed to be placed in a ramp of a given size, or how should packages of food be distributed to laborers. Like depending on how many laborers you had, how much food did you need to feed them? These were kind of some of the basic concerns. What era is Egyptian math representative of? So the Rhind Papyrus is from about 1650 BC, and the Moscow Papyrus is from 1850 BC. So you might say, why do we begin with Egyptian mathematics? So the ancient Greeks actually believed that math came from Egypt, and one of the earliest Greek philosophers and Greek mathematicians was Thales, that the book is named after. And the story is that Thales actually brought back both the study of math and geometry to Greece from Egypt. He went to Egypt on a trip, and he stayed there for a couple of years, and when he came back, he brought with him this knowledge he learned from Egyptians. So I'll go ahead and write these. There's the Moscow Papyrus. So Moscow Papyrus is called that because it ultimately ended up being purchased by the Soviet government, I believe, in the... Oh no, actually it was no. So before that, it was acquired by a private individual in 1893. Yeah, so this was still under the Tsar. So the Moscow Papyrus is approximately 1850 BC, and the Rhind Papyrus is approximately 1650 BC. So the author of the Moscow Papyrus is, I am not sure if it is known. The author of the Rhind Papyrus, however, is Almos. Okay. Now, the idea is that the Greeks believed that Egyptian mathematics, or Egypt was the source of math. Like it was basically the first place that did real math or real geometry. Now we know that the Sumerians also were really, really early in their development. So Mesopotamians were really, really early in their development of mathematics. So whether the Egyptians or Mesopotamians were, which one was earlier is hard to say. We have more, I believe we have more. Well, we have two original sources of Egyptian mathematics, and I believe both of these date to earlier than the sources of Mesopotamian mathematics, although I'd have to check that to be sure. I will say that there's inferences that can be made based on documents we have that, even though we don't, there's an issue here, and there's a reason why the Greeks play like a pivotal role in the history of math, and we will talk about this at length because it's extremely important. But it is very difficult to pin down historically who discovered a concept, right? And of course, I carefully chose the word discovered rather than invented, right? This is a philosophical question of, is math invented or is it discovered? So I'll say discovered. Maybe you think it's invented. But the idea is that the reason that the Greeks are so important is because before the Greeks, saying that one civilization or another discovered a mathematical concept for the first time is tricky because they would just use things. So, for instance, the Egyptians would use, say, the distributive property of numbers, right? But nowhere were these things stated logically, and nowhere were things proved or their assumptions stated. And so it can be hard to nail down. For instance, it's like, okay, did they know this fact and they just kind of assumed it to be true? Did they know this theorem, right? Did they know the Pythagorean theorem? That's going to be a question we talk about, whether or not the Babylonians knew the Pythagorean theorem or not. Because the point is there are instances where earlier mathematicians, both Egyptians and Babylonians, actually used some fact, right? But they didn't actually state why they could use it, and they certainly didn't prove it. And so, are there examples of basically the Pythagorean theorem being used to solve some things in Babylonian mathematics? Yes, but there's certainly they didn't write down any proof of it. And the reason why this is such a big deal is because when you write out a proof of it, right, that's when you are like setting down logically, like the relationship between the logic used and the computations that you're doing. And it also allows for generalization. It allows for the types of questions. You can ask questions that are more far-reaching if you understand what is needed to prove something. And so, anyway, getting back to this question of Egyptian mathematics, the Moscow Papyrus has, there's an example listed of, so maybe I'll do this first. So the Moscow Papyrus lists an example is computing the volume of a truncated pyramid. Okay, so there we go. So computing the volume of a truncated pyramid. So you can I know you can look up scans of the Rhine Papyrus online. I'm not sure about the Moscow Papyrus. I didn't look it up immediately before lecture, but I might actually do that right after. So computing the volume of a truncated pyramid. So what is meant by this? So imagine a square-based pyramid, right? I don't think I'm even going to bother trying to draw one of those because it'd be better if you just imagine. So imagine I have a square-based pyramid in front of me. And I am interested in computing not the volume of the entire pyramid necessarily, but the volume of that pyramid where I've taken the top off. So I've sliced off the top via a plane. So imagine a plane cutting through a square-based pyramid that is parallel to the square base. Okay, so it cuts through parallel to the square base and takes the top clean off. And what I'm left with is a square-based pyramid that's top has been removed. Okay. And so let's say that you have a square-based pyramid, and the square of the base has length A. So the square of the base has length A, and we'll say that the length, has side length A. So any side of that square has length A. And we'll say that the square that results, so to check that a square results, right? You have square-based pyramid. What are the cross sections, the parallel cross sections of a square-based pyramid look like? Because the pyramid is a square base, they all look like squares. But they are squares of, they're getting smaller and smaller and smaller as you reach the apex point of the pyramid. You can imagine, right? There's a plane that's tangent to that apex point that's just a point. But if you take that plane and just bring it down a little bit, you just get a tiny, tiny square. Okay, so if A is the length of a side of the base square, and B is the length of a side of the top
square. What is the volume of a truncated pyramid? The computation that is done in the Moscow Papyrus showed that this volume is h over 3 times a squared plus ab plus b squared. So A is length of base side. B is the length of the top. Length of the top face. Okay, and H is vertical height, not the slant height of the pyramid. This is the vertical height of the pyramid. So this is the height that goes from the center of the square in the bottom all the way to the apex point, right, vertically. Okay, and so this is the volume of a truncated pyramid is this thing. Now that's kind of an interesting formula, but actually to see that this is the same formula as the volume for a regular pyramid, if I take this truncated pyramid, but I actually don't truncate it at all, if I don't cut off the top at all, then what could I say that the side length of the top square is? Well, in that case, b is 0. And so if b is equal to 0, what do I get here? Setting b equal to 0, both of these terms are 0, and what I get is that the volume is h over 3 times a squared. But what is that? This is the volume of the complete pyramid, right? This is the volume of the whole pyramid. Okay. So that's interesting. And apparently that's the most interesting part of the Moscow Papyrus. Now, of course, it's Egyptian mathematics. It's only natural that pyramids show up. But a question is, why did the Greeks think that the Egyptians invented or discovered mathematics? Or I guess what was their rationale for this assumption? So I believe Aristotle thought that. So Aristotle's belief was it was developed by the priest class in Egypt because the priests were basically the first people in Egypt to have free time, where they were just sitting around bored and did math to entertain themselves. Herodotus actually thought that it was mostly because of their proximity to the Nile and the fact that the Nile had this periodic, very predictable flooding that allowed them or it gave them a reason for needing to be very thorough with land surveying, which is why the Egyptians supposedly discovered geometry. Was they needed to understand these geometric quantities because of literally measuring off land boundaries and stuff, pre and post flood that happened annually, this flooding of the Nile. So in fact, I believe Democritus actually called Egyptian mathematicians rope stretchers for this reason. So for this reason, the Egyptian mathematicians were called rope stretchers because of the relationship between the math that they did and the measurement or surveying of land. So it makes sense that the earliest mathematics would have evolved out of kind of a basic need for humans to count and do mundane things. But of course, what always happens, right? You begin with the development of math as something meant to just keep track of mundane things, like how many cattle I have, how many measuring land boundaries, right? Just enough geometry to get you by to allow you to do that efficiently. And then all of a sudden you start noticing patterns, right? And you notice that there's these patterns that exist, and they exist in different situations, and that's what allows you to make observations about some theorem, some mathematical fact. It's, oh, here's a statement that is true not just in this particular situation I'm in, but it's true in general, right? It's not just true in my situation, it's true in this other situation that is different but has these properties that makes it true in this other situation. And so that's the the power of math to generalize, right? So we'll be doing this a lot, jumping back and we will use the fact that we know modern math to go back to ancient math and give us better insights. There's no reason to pretend like we're learning all this stuff for the first time. So for instance, when you talk about a partial differential equation, there's the diffusion equation, right? Or classically it's called the heat equation. The point is that it didn't really matter whether the equation was modeling heat or diffusion of, say, some chemical in another chemical. It didn't really matter what it was modeling, whether it was heat or diffusion in general. The underlying mathematical model was the same. So like think of, that's a pretty powerful statement that the exact same equation, right, is used in vastly different settings. That's something you take for granted, of course, when when you've studied math a bunch. You kind of take for granted that something so obvious or obviously true that math can do is actually pretty amazing. Okay, so this is the contents of Moscow Papyrus that I wanted to mention. The Rhine Papyrus is very interesting, and you might have seen this before because it's actually so famous that it has received a lot of attention from like pop math stuff. So what's the contents of the Rhine Papyrus? So again, I'm going to bring this back onto the screen. So this, for instance, is like a block of the Rhine Papyrus. Okay, what is being done here? Okay, well, so Egyptians actually used a number system that was base 10, and we'll talk about number bases next time. But they used a number system that was base 10. Meaning that these symbols were grouped in blocks of 10. Okay, and so in fact, this is a 10, and these are two ones. Okay, and these two are each 10, and these are 4 ones. And these are 4 10s and 8 ones. And here's 9 10s and 6 ones. So these are 1, this is 2, this is 4, and this is 8. And I have some marks here, and then I have the weird symbol here. I don't know what that is, right? So, okay, so what's going on here? Let's translate this. Okay, let's translate this picture, okay, using that. If I tell you that, these are 10s, these are 1s, and if I tell you that this is the symbol for 100, well, now I can make this full translation. So what do I have here? Let's translate this into our notation. So this is 1 10 and 2 1s. So that is the number 12. All right, so that's the number 12. So 1 10, 2 1s, that's the number 12, and that's a 1. Okay, what about the next entry? I have 2 1s or 2 10s and 4 1s. So that's the number 24. And next to that, I have 2 1s. So that's the number 2. And then I have 4 10s and 8 1s. So that's 48. And then I have 4 1s. So this is 4. And I have this dash here, which is a check mark. Okay, so I'm going to go ahead and put that check mark here, okay, or that mark. All right, next I have 9 10s and 6 1s. So 96. And then this is 8, and I have another thing checked. And then out from this, what do I have here? I have this symbol, which I said is 100 here. This is 100, 4 10s and 4 1s. So this is 144. what is being done here? What is this computing? Well, let's think. What is clearly going on here? In each column, what is happening? Well, in each column, I started with a number, and I doubled it a bunch. So I started with 12, and I doubled it and got 24. And I doubled that, and I got 48. And I doubled that, and I got 96. And then I did the same thing here. Okay, but what's the difference, or what's the deal with these check marks and this 144? What this table does is it computes 12 times 12. How does it compute 12 times 12? It starts out with 12, okay, and it doubles it, okay, until I have doubled it, keeping track of how I'm doubling it, right? So I started with 12, that I put a 1 next to that, and then I double that until I get an 8 and a 4 here. Why do I care about that? Because 12 times 12, I know, is 12 times 4 plus 8. Right? Well, I know that I have the distributive property. So really, 12 times 12 is 12 times 4 plus 12 times 8. And then I can read off this table here. By just doubling this thing, I get 48 after I've doubled twice, but doubling twice is the same thing as multiplying by 4. The right column, as someone said, yeah, the right-hand side's the multiplier. It's what you're keeping track of as multiplying 12. So when you just have 12, you're multiplying by 1. When you double it, you're multiplying it by 2. When you double that, you're previously multiplying it by 2, but you multiplied it by 2 again, so you're multiplying 12 by 4. And so 12 times 4 here is 48. And 12 times 8 is 96. And so this is 48 plus 96, which is 144. And so what entries are getting checked here, right? So what entries are getting checked are the entries that sum to 12. Right? Now, could you do this for any pair of numbers you're multiplying? Does this always work? What if I did, let's do 17 times 22, right? Like 17 times 22. How might I do 17 times 22? Right. So someone said, did the Egyptians know that multiples of 2 could add to any number? So this is an example of one of these things. It's like, because they showcase these exercises, they seem to know that this always worked. And they seem to know that this always, like, why does this always work? What is it that you need here, right? The sums of powers of 2 alone is not going to get it to you. You need this 1 sometimes. Right, so let's do 17 times 22 by actually doubling the 22. Right, so 17 times 22, we're going to double the 22 instead. So we start out with 22, that has a multiplier of 1. And then we double that, so that's 44. That's 2. And we double that again, so that's 88. That's 4. And then we double this, so what is that? That is 160 plus 16, so that's 176. That's 8. Now, adding this would only give me 15 total. So, of course, could you add, there's many ways that you could do this, right? So you could add this to itself twice and then add 1. Let's say that, I didn't even see that. Of course I could do it that way, right? I could add 2 copies of 176 and then 22, and then I'm good. But I'm gonna double this one more time. So doubling this one more time, I would get, so when I double 176, what I get, so that's 340 plus 4, so that's 352, right? Okay. And then, so 22 times 17, right, is, I can do this by adding 16 and 1. So 22 times 17 is 22 times, 16 plus 1, which is 22 times 16 plus 22 times 1. So this is 352 plus 22. So this should be 374, right? Okay. Now, what is the benefit of doing this? Um, there's actually, depending on the numbers that you're multiplying, um, this can, and you can try this just in your head. It can be pretty quick to do it this way compared to, like, say, the standard algorithm. The problem with the standard algorithm, right, is that the standard algorithm for multiplication of two numbers gets you there in a very short number of strokes of a pen. But if you're doing it mentally, keeping track of everything in standard algorithm is actually kind of terrible. Of course, you can do it, but it's actually much easier to use these kinds of properties. Now, the Egyptians, didn't just use powers of two. So this was the most common method, but they would also intersperse this with multiplying by 10. Now, why would they multiply by 10, right? Why would multiplying by 10 even be nice? Well, because they used a base 10 system, right? So, as we'll talk about next time, when you use whatever base of a number system you use, it is easy to multiply by that base. So if you're a base 10 system, then multiplying by 10 is the easiest possible multiplication you could do. Now, I've run out of time. I realized I was talking for too long there, so that's all I'll say for today. But on Wednesday, we'll start here. I'll finish up this bit about Egyptian math, and we'll continue on. I'll talk about number bases and things like that. So anyway, be on the lookout for the syllabus. I'll post it sometime. It'll be later tonight, and I'll let you know when it's posted. So you can have a look over that, and if you have any questions after that about the outline of the course, then just let me know. So going to be going at a pretty, leisurely pace. So, we've got plenty of time. If you have any questions or concerns, you can just let me know, and I'll get back to you as soon as I can. But otherwise, I will see you all on Wednesday at 3. So have fun, and welcome to the course.